Okay. Okay, so these different kinds of groups with different properties. We learned about metals versus non-metals. We learned about so metals always want to get rid of these electrons, right? While non-metals make usually more covalent bonding. Noble gas is very unreactive. We talked about the naming of binary compounds, right? Let me just directly go to the scheme. So we have these type 1 and type 2 binary compounds. Type 1 where the cation has like a distinct charge state always, no matter in which compound it is. Like sodium, it's always +1. So we don't need to like think about the charge state. Sometimes we have something like copper which can have various charge state, then we need to use the principle of charge balance. So the whole compound should be neutral, and then we can determine the charge of the cation. And then we talked also about compounds. Okay, just go further with more than binary. So we have like more atoms. So ions which consist of multiple atoms. And in that case, we had to memorize a couple of these names, right? We have this table here with all the different names of the anions which you need to memorize. And then we learned that we can otherwise use that in exactly the same way to name them. We have to also keep in mind that we need to then number the anions. Like if we have several of them, of these, then we usually number them with mono, di, and so on. Okay, and otherwise this was this. So this is this type 3, right? Where we use these prefixes and certain notations. They still call this binary, sorry, they still call this binary because we have one cation and one anion. But in this case, we didn't have a metal, so that's why we use these prefixes. Like, okay, and polyatomic anions, we need to use these names we need to memorize. Okay, so now we go on with the next topic for naming. So naming is quite boring, right? I hate it also, like learning about such things, but we will use it in practice at some point. So it's good to have a common convention among us how to name things. So another category of compounds that we consider here is acids. Acids are compounds which have protons in there. So last time I told you proton H plus is a proton, right? It's a hydrogen atom. If you remove the electron, you're left with one proton. So you can just call this a proton, right? It's just a proton. And if you connect this proton to chemical compounds, you make acids. One example we discussed last time, we have ammonia, and we react this with the proton and form this ammonia. Remember this, right? This kind of, it's called tetrahedral form. So one of the hydrogen goes to the back, so they make some kind of pyramid, and then one hydrogen points up. We call this a tetrahedra. So why this one we would actually call an acid? Why? Because it can actually give the proton away again, and it can become ammonia, right? So an acid, we have different ways to define acids, but one way would be saying something that can donate protons. Yeah? Would be, for example, this is called usually the Britsted acid. We will later realize in this lecture there are different ways to talk about acids. So compounds which have protons which can be donated to something else, we will call for the moment acid. And then if the anion contains an oxygen or not, the naming is a bit different. If the anion ends with IDE, the acid is named with the prefix hydro and then the suffix IC. When the anion contains oxygen, based on the nature of the anion, the acidic name is formed from the root name of the anion with ICO. So it becomes more and more complicated, this naming, right? So let's actually just look at an example. If the anion ends with ATE, then IC is added to the root name. If the anion has an ITE ending, the ITE is replaced with OUS. Okay, so let's see. The first one is HF, which is called hydrofluoric acid. Right, so we have fluoride. Fluoride is the anion name. It ends with ITE, then the acid is named with hydro and ic, right? So that's why it's called hydrofluoric acid. Yeah. Then, of course, these are exactly the same, HCl, HBr. These are all halogenides. They are all with IDE fluoride, bromide, and so we just add hydro and IC acid. Okay. And then we have here hydrocyanic acid, same way. In this case, cyanide, anion, and sulfide, anion. All of these are ide anions, so it's just the same convention. Just add hydro to it for indicating the proton, and then IC acid. Okay. Now these are a bit different. These have oxygen in there. So how do we deal here with this? What did we say? When the anion contains oxygen, based on the name of the anion, the acidic name is formed from the root name of anion with the suffix ic or us. Okay, and we will use one of the two. If the anion ends with 8, we will call this ic. Okay, so this is nitrate, right? Nitrate anion. This is what you need to learn also. Nitrate, ATE. Okay. In the case of ATE, we will turn this into ic. Okay. So it's nitric acid. Yeah. To be honest, you can also just memorize this. You don't need to memorize the rules, no matter depending on what is simpler for you, because these are the most important ones. So I think the rules are somehow not that consistent, but well, anyways. So you have nitrate, sulfate. So both of them are called nitric acid, sulfuric acid. Now this is nitrite, so you turn this into nitrous acid. Sulfide, so you turn this into sulfurous acid. Phosphate, phosphoric acid, and acetate, acetic acid. Okay. 8 always becomes ic, ide becomes us. Okay. So flowchart for naming the acids. You determine if the anion has oxygen. If not, then you use hydro plus the anion root plus ic, right? If it contains oxygen, you need to check the ending if it's ide or 8. If it's 8, you use ic. If it's ide, you use us. Okay. So based on this, we can try this one more time. Name a couple of compounds from all the rules that we did so far. So the first one is a copper with iodide, anion, right? So what is the oxidation state of copper here? What is its charge state of copper? What would be the... What is the charge state of copper? Copper iodide? +1, right? Iodide is -1. So copper has to be +1, so then it's balanced, right? So it would be copper 1 iodide. How about the second one? So in this case, we have like a sulfur and we have a nitrite. It's a non-metallic compound, right? In non-metallic compound, we have to count how many atoms we have, right? It's a tetra here, tetranitride. and tetrasulfur. So we call this tetrasulfur tetranitride. Next one, sodium, and then we have the anion here, and the anion here has a hydrogen in there, right? So we call this sodium hydrogen carbonate or sodium bicarbonate. Usually everyone will say bicarbonate, but this is kind of like a trivial name. This would be the UPEC nomenclature. And this is another one, barium. So how do we name this one? This has a chromate here, so it's a barium chromate. Okay. Just some examples here. Okay. So which is not the correct chemical formula for the compound named? A, potassium phosphate. So who thinks this is the right name for that formula? Who thinks this is wrong? I just gave you a minute. I want to see more hands. Potassium, what is the charge state of potassium? Is it flexible or is it always the same? Always same, right? So we don't need any Roman numbers, right? We don't have Roman numbers, that's fine. So who thinks this is correct? Who thinks this is not correct? Oh, hey, why are there no hands today? What's going on with you guys? I need more hands, otherwise I cannot continue. Just look at your rules one more time. Already standing for 2 hours. Okay, do you think about it? Who thinks this is correct? Looks a bit better. A couple of more hands. Still could be more, but okay. It's correct, right? Potassium, it's a metal. We don't count like how many metal atoms we have, right? We don't need the Roman letters because it's always +1. And phosphate is the right name for PO4 3-. It's PO4 3-, so it's correct that there are 3 potassium atoms. How about second name? Iron 2 oxide. Is this the right name? Who thinks this is the right name? Okay, wrong name. Okay. It's correct, it's the right name. 2 means charge state 2, right? Oxygen has to be, is also -2, so we just need one of them, right? How about C, calcium carbonate? Who thinks this is right? Yeah, it's right. Next one, sodium sulfide. Who thinks this is right? Thinks this is wrong. Okay, so it's a bit more for wrong. So why is it wrong? The sulfide is in the same group as oxygen, right? So how many electrons does sulfur likes to get? 2, right? Then it becomes noble, right? So it should be 2-, right? But if it's 2-, then we need 2 sodium, right? Because sodium is +1, right? So it should be Na2S, right? That's sodium sulfide. Okay, and the last one, lithium nitrate. Who thinks this is right? Okay, yeah, so it's enough for me. So nitrate is -1. It's also correct. Okay, one more round. A Li2O lithium oxide. Who thinks this is the right name for this formula? So this formula is given and you should judge the name, right? So who thinks the name is right? Yeah, most. Right, it should be right because lithium oxidation state is always +1. We don't need any Roman number. Second one, FePO4. Is it right that this name is iron 3 phosphate? Who thinks this is right? Who thinks this is wrong? Okay, agreed. It is correct name. C, HF is hydrogen fluoride. Who thinks this is right? Yeah, also most are right. So this is pretty simple. This is always fluoride. We just add the H here. The next one, BaCO2 is a barium dichloride. So who thinks this is right? Who thinks this is wrong? Okay. So why do you think it's wrong? Who said it's wrong? Why do you think it's wrong? Can someone explain it?
The prefix di is for non-metal.
That's right.
Copper.
That's right. So di you only use it for the non-metal, but you have a metal here, barium. So you would just barium chloride, right? And the last one, Mg3N2, magnesium nitride. Who thinks this is right? Thinks this is wrong? Okay. So a little bit confusion about this one, but this is actually also not that difficult. Magnesium is +2 always. You don't need any Roman numbers there. And this is nitride. It's N3 minus, right? So, and since this is a metal, again, you don't need to count them. So it's exactly the right name. Okay. Which is the correct formula for copper 1 sulfide? Who thinks it's A, B, C, D, E? Okay, yeah, it's B because so for copper is a 1 charge state, so 2 of them will make it +2, sulfide is -2. Right? Which of the following is the correct chemical formula for iron 3 oxide? A, B, C, D, E. Yeah, I think you all got the idea now. Just do the charge balance and then you have it, right? Okay, so one more. What is the correct name for Mg3PO42? Who thinks this is A, trimagnesium diphosphate, magnesium 2-phosphate, magnesium phosphate, magnesium 2-diphosphate, magnesium 3-diphosphate. Okay, so it's magnesium is always +2, so you don't need any Roman numbers here. And since it's a metal, you don't count, so it's just magnesium phosphate. What is correct name for acid with the formula HFO? Is it A, fluoric acid? So who thinks this is fluoric acid? Fluoric acid is just HF, right? Who thinks this is hydrofluoric acid? Who thinks this is hydrofluorous acid? Hypofluorous acid. Perfluoric acid. I just introduced the rules for you for the naming of the acids. So, but we didn't do this example, I think. So this anion is actually called hypofluorite. Hypofluorite. So hypo because it has just one oxygen there. This is a bit tricky one, I think. And the ide will turn into us. So D is the right answer. Actually, hypofluorous acid. but I think you didn't do the FO minus anion, so I think it was not in the list of names. Was it? Hypochlorite was maybe in the name. And hypofluorite would be similar, right? Maybe. Okay, then let's go on to the next lecture. Okay, so this lecture will be about stoichiometry. So based on our knowledge now about chemical formulas, which tell us about how many atoms are in a molecule, right, of each element, we can actually learn how to calculate with that. We can learn how to calculate mass ratios from the stoichiometry. So stoichiometry basically just means the ratio of the elements. So here, the stoichiometry is just N1H3. Yeah. 1 N atom, 3 H atom. That's meant with stoichiometry. So we can use this one to calculate masses. We can learn about the mole, the unit of mole, which is very important for chemistry. And we do a couple of problems as always. We will look into balancing chemical equations and doing some stoichiometric calculations with the chemical reaction equations. Okay, so what is chemical stoichiometry? It's a study of the quantities of material consumed or produced in chemical reactions. So the stoichiometry of this NH3 will be 1 and 3, and then discussing basically like how many of these atoms are converted into another compound. That is what we talk name as chemical stoichiometry. So this actually helps us to determine, to calculate the yield of a reaction, for example. So let's say we use for this reaction 1 gram of ammonia. We can calculate how much gram of ammonium ions we produce because of this chemical equation and because we know how many atoms are in each compound, right? So we will learn how to do that. So when we talk about the mass, then usually we talk about the average mass of objects that is required to count the objects by weighting. For the purpose of the counting, the objects usually have to behave as idealized. And samples of matter can contain a large number of atoms, right? And the number of atoms in the sample can be determined by finding its mass. So usually we idealize the sample. We say the sample consists of, let's say, 1 trillion molecules, and they are all the same. There's no like dust in the sample or any kind of like dirt, right? Which would like, of course, have an influence on that calculation. But usually we would just assume that we have the same molecules all over the place, and then we can directly convert the mass to the number of atoms that is in there. For this, it's quite useful to introduce another unit when we talk about the mass of atoms. And this unit is called U. You remember maybe the mass of a proton, right? It was really small, like 10 to the power minus 27 or something. So we don't want to always calculate with these very small numbers. So the people said, okay, carbon atom, carbon is has like a 12 total numbers of protons and neutrons. So let's just define this as a mass of 12 U. Yeah. So a carbon atom has exactly the weight of 12 atomic mass units, which we call U. And for all the other atoms and elements, we just calculate it relative to the carbon atom. Yeah. So based on this, because we know how many protons and neutrons the carbon has and how much they weigh, we can also calculate the U weight of a proton and a neutron, right? And then we can convert to any element that we want, and we can calculate their mass in U. How do we actually measure the mass of atoms? You remember there was this experiment, the Thomson experiment, right? Where we we're able to measure the Q over mass ratio of an electron, right? We kind of fired out these electrons from the sample by applying an electric field, and then they went into another field and they were deflected, and their position was determines the Q over mass ratio. And this is essentially how the mass spectrometer works. So you have a sample here, and then you have an electron beam which ionizes your sample. So if you have a molecule before, then this will become an anion or cation after this. Why do we do this? Well, because if they are anion and cations, we can accelerate them in an electric field. If they are neutral, we cannot, right? So we want to accelerate them, and then we have a magnetic field to deflect them in the direction. And then their position on the detector will exactly depend on the mass over charge ratio. Yeah. So with this instrument, you can put any molecules into this sample. You ionize them, and you just detect them based on their mass ratio. So you can split a sample based on mass over charge ratio. So this is very, very powerful, and it's used still up to date as probably the most reliable instrument to analyze chemical compounds. And there are also different variants of this, because you can maybe imagine ionizing a compound by bombarding electrons with it might lead to some chemical reactions, right? And in fact, that's true, and it can lead to splitting of the molecule into fragments. So interpreting this would be quite difficult. You need to know what kind of fragments you can form and so on. Okay, and this is basically what I just explained. So this is how it then looks in practice. So you have like this sample here, you ionize them with an electron beam. So this is a heated filament where the electrons shoot out, and then it goes into this slit to get like a more focused molecular ion beam, and then it goes into the magnet where it eventually splits into that charge to mass ratio, and you detect it. And well, you can use this to determine accurate mass values of individual atoms, but also you can use this to determine the composition of molecules and masses of molecules. You can determine what kind of molecules you have, but also if you have like very large molecules, like proteins, they will usually decompose into various fragments. And by knowing what fragments you have, you can get information about your structure of the molecule, right? So mass spectrometry can give you a lot of information, not only the mass, but also the information about the structure as well. There's one thing that we do need to know when we talk about masses, is that all the elements that occur in nature, there will be mixture of their isotopes. Yeah? So if we talk about carbon, carbon has carbon-12, carbon-13, carbon-14. All these isotopes will occur in nature, but to a different ratio, right? So if we do an experiment, let's say with carbon dioxide gas, we have to know that the mass of carbon, the average mass of carbon will be the average of all these isotopes. Some molecule will have a carbon-12 atom in it, another molecule will have a carbon-13 atom in it, and on average, we will have a certain mass that we can get by averaging these isotope masses. Yeah? So that is the idea behind it. So we can take the mass of 12 carbon. The mass of 12 carbon is just 12U. That's how we define it. And in the nature, it appears as 98.89%. So most of the carbon is actually carbon-12. Carbon-13 has only an occurrence of 1%. So carbon-13 has of course a larger mass. Why is it not exactly 13? Any idea?
Neutron is slightly heavier.
Sorry, can you say?
Neutron is slightly heavier.
Right. So the mass of the neutron and proton is not the same, right? So adding in a so we don't have exactly like 1 U of weight for a proton and a neutron. They are slightly different in mass. So if we add a neutron to it, it will not exactly be 1 U. It will be a little bit different. But the mass is roughly 1 U for one proton and neutron, but not exactly, right? So that's why it becomes a little bit different. Okay. So if we would want to get the average mass for our calculations, we just take like the occurrence of that 12U. It's 98% times 12U. We add 1% times 13.0034U, the mass of carbon 30. We add them all together, and we get 12.01U. Obviously, it's almost entirely determined by the 12 carbon, but there's a slight deviation, right? In this case, you would say, do we care about 0.01? Well, sometimes we might, right? If we, depending on how many significant figures we're interested in, right? And there are other elements where the mass of the isotopes is much closer together in terms of the, because the occurrences are much similar. In that case, the weight would be like, easily can be like 0.5 or something like that. Okay. So we will usually then, when we do the calculations, use this number. And this also you can see in the periodic table. Below the carbon, there is 12.01. This is the average isotope mass. Yeah. So these are the masses in U that you usually will use when you do any calculations. Yeah. Okay, this is another example. So here you're given an element, you're given the occurrence ratio of these different isotopes. 1.4% of this mass, 24% of this, and you see these isotope masses are much closer together, right? So it's really important to account for the correct ratio. And then you just average this mass. And by averaging this mass, you get 207.2 U. And then you can look into the periodic table and you can see what it is. And it is lead, Pp. Okay. So this is how you can, so by measuring the mass, you immediately will know what element it is. In the mass spectrometer, also you measure the average mass, right? Because the mass spectrometer has like thousands and millions of molecules shooting on it. So you will get a signal at both isotopes. And then if the mass spectrometer is very accurate, you can even resolve the two isotopes. But if not, they will just appear as an average peak, right? That then depends on your mass spectrometer, how accurate it is. Okay. So this is a mass spectrometer which can actually resolve these isotopes. So you can see the mass number here of two of the two copper isotopes, copper 63 and copper 65. And the relative number of atoms is directly indicated by the signal, right? So the higher the signal in the mass spec in relation to the other, the higher the occurrence is. So you can directly infer from this the relative ratio of this. Okay, so what are we going to do here? We want to calculate the average mass of natural copper. And we know that the mass of copper 63 and copper 65 are given like this. And how do we then calculate the average mass? Well, from the mass spectrometer, we know the occurrence. So we just have to multiply them with this average masses, right? So we take the okay, so this one is not really necessary. Okay, so you would basically take like the ratio here and you multiply it by the atomic mass and then you would get the average mass. Okay. Just take this one. Okay. So let's do a join in here. The atomic number of indium is 49, and its atomic mass is 114.8 grams. So what they mean here now is the actual mass of your sample, right? 414.8 grams of your sample. So a naturally occurring indium contains a mixture of indium 112 and indium 115 in an atomic ratio of approximately, and that's the question now. So what is the ratio of these naturally occurring isotopes that you need to take in order to get this atomic mass? Okay, so you can think a moment about this one. So let's actually take this as 114.8 U. I don't know why they wrote gram here. Let's say, okay, atomic mass of 114.8. Okay, so the average mass is 114.8 U. So what is the ratio we need? That's the average mass. And what is the ratio you need in order to for these two isotopes in order to match this number? So you can roughly calculate with that, with the isotope, you can roughly calculate this as 112 U to calculate it. Actually, you don't even need to calculate, you can just estimate it. Like, just right here. So we have okay, so who thinks the ratio should be 6 to 94? Yeah. This one, B, C, D, E. So you can see the average mass is really close to indium 115, right? Which means that the ratio should be this one. Without actually calculating, you can know this one, right? Because, yeah, you have much more weight on this one. Yeah. Okay. You have a sample of zinc and a sample of aluminium. Each sample contains the same number of atoms. Which of the following statements concerning the masses of the samples is true? Okay, this is about text. Numbers of atoms of aluminium and zinc are the same, right? So I just write this as a big N for the number. So A, the mass of the zinc sample is more than twice as great as the mass of the aluminium sample. So you probably need to look now at the masses of one atom, right? So look into the periodic table, zinc and aluminium. So what is the average mass of zinc? 65. What is it? 65. So let's just write 65 roughly. 65 U. And the mass of a zinc atom is roughly what?
You wrote zinc twice.
Twice.
You wrote zinc twice.
Oh, so what did I write? Actually, let me make some space. Otherwise, my writing becomes worse and worse. Let me just make space. Okay, so what is zinc?
Roughly
65. And what is aluminium? 7. Okay. So these are the average mass of one atom. And we have the same number of atoms. So the mass of zinc sample is more than twice as great as the mass of aluminium sample. So who thinks this is right? Yeah? So a lot of people think like that. You have the same number of atoms, but zinc is double as heavy as aluminium, right? So that means also the sample should be double as heavy, right? Makes sense. So this is correct. And I think the others we don't need to do because they are basically the same, just inverted, and they are wrong. Okay, now maybe you would ask the questions, how many atoms we actually have in our sample? And you will see that this will be in order of like 10 to the power of 23 atoms. So the n would usually be in that order. So it's usually a good idea to introduce a number as well for that, another unit, which will be more useful for us. So this is called the mole. And this equals to the number of carbon atoms in exactly 12 grams of carbon 12. As again, we use carbon 12 for the same purpose. This number is 6.022 to the power of 23. So 1 mole is this number of atoms. For this purpose, we usually introduce the so-called Avogadro number. Avogadro number is 6.022 times 10 to the power of 23. And the unit here would be per mole. Okay? So this is the number of atoms we have. And we introduce also another symbol, which is the small n. The small n is the number of particles over the Avogadro number. And this is measured in mole. This is the so-called mole number. Okay? So we divide the number of particles by number of particles per mole, and we get mole, right? This is mole minus 1. This has no unit, so we get mole, right? So again, make sure to get these units right. And then we can also realize another thing, which is if we take the mass of the cell, we take the mass of the sample and we divide it by the number of moles we have, that would give us the mass per 1 mole, right? Mass per 1 mole of particles. This is what we usually write as a big M. This is the molar mass. Okay, this would be measured in gram per mole. So now comes the question, what is the molar mass of carbon 12? 12 gram per mole. Yeah. And that's exactly the reason why. It was 12U before, right? But now we exactly define the number of particles in 1 gram as the Avogadro number, as 1 mole. And that is why the mass of carbon is also exactly 12 gram per mole. Because we just define the mole exactly like that. Okay. Okay, so this will be very useful for us, these equations, to calculate with this. This is 1 mole samples of several elements. You can see how different it is depending on the element. And of course, depending on the molar mass, right, it will be more or less, right? If the molar mass is really high, then for given 1 mole, you have like a, sorry, what did I say? High molar mass. So you have a lot of mass for the same mole number, right? So you would have like a lot of mass, right? Okay. These are a couple of numbers of atoms is always fixed to 1 mole, and then the mass of the sample. So you can see mercury has a very high mass for 1 mole, so it has a very high molar mass, right? While aluminium has a very small molar mass. Now it's important to know the difference, right? Here we are talking about a block of metal, right? This is different from just atoms. So the atomic mass is always based on a single atom, right? The molar mass also depends kind of like, no, it doesn't depend, sorry. It's the same thing, so we just count the number of atoms. And each atom contributes the atomic mass, and then we get the total molar mass per sample. Forget about what I just said. Okay, so how do we calculate with this? So 12 gram of carbon-12 contains exactly 1 mole atoms, and 12.01 gram of natural carbon also contains this amount of atoms, right? Just in a different ratio of carbon-12 and 13. And the ratio of masses of these samples is the same as the ratio of the individual components in U, and both samples contain the same number of atoms. So mole is defined such that a sample of a natural element with a mass equal to the element's atomic mass expresses in 1 gram contains 1 mole of atoms. And it sounds very complicated, so I think you don't need to really think about it like that. Just think about this formula, right? Mass for 1 mole atoms, that's the molar mass. And typically we don't need U for any calculations. Typically we always need only the molar mass. But this is how you can see it, right? You multiply the number of atoms in 1 mole by the 12U per atom, and the atoms cancels out, and you get the mass in U, or you can convert also into gram. This would be exactly 12 gram. Why is 12 gram? Because we define 1 mole like that. Right? 1 mole of atoms with 12U each is exactly 12 gram. Right? And now you can see this gives you then the molar mass of 12 gram per mole. Yeah. Okay. Okay. Okay, so one interactive example here. Cobalt is a metal that is added to steel to improve its resistance to corrosion. Calculate both the number of moles in a sample of cobalt containing 5 times 10 to the power of 20 atoms and the mass of the sample. Okay, so you're given the number of atoms. You have to calculate the mass and the number of moles, right? So we just need to use these equations here, right? We have N, the number of atoms is given. Na we always know, it's the Avogadro constant. Just divide it, you get the moles, right? Once you have the moles, then you can solve this equation here for the mass, right? Because the molar mass we know, multiplied by N, you get the mass, right? So these two equations are probably the most important equations in this lecture because they are most important equations for the chemist. You need it for almost every day to do conversions. Okay, so they use a bit different way. Like in this book, they don't like equations and symbols. I don't know why, but I like symbols. That's why I introduced it to you like that. But the way that they calculate is, of course, exactly the same way. So what do we know? We know the number of atoms. And how do we get there? Well, we have to know that 1 mole is 6.022 times 10 to the power of 23 atoms. So divide by that, and we have the number of atoms per mole, right? This is the atoms, divide by the number of atoms per mole, which is the Avogadro constant, and you get the moles. And now, once you have the moles, you take the molar mass, which is 58.893, and then you just rearrange that equation and calculate it, right? So it goes like this. So you have the moles, and you just multiply with the molar mass to get the mass, right? Okay, so just multiply n to the other side, right? Okay, and then you can. It's always good, and this is actually something which I also personally find really important. When you calculate something, right? Always think about, is it realistic or not, right? Because if it's not realistic, it's very likely that you did a mistake, right? So units and checking if the results is realistic are really good to find your mistakes, right? So always check that. So what do they mean with reality check here? Well, the sample contains 5 to 10 to the power of 20 atoms, which is approximately 1,000, fraction of 1,000 of a mole, right? So the mass should be around 3 orders of magnitude smaller, a factor of 1,000 smaller of this original mass, molar mass, which is around 0.06. And you see the result is kind of matching that. So it kind of makes sense that this order of magnitude kind of makes sense. Okay. Another exercise, diamond is a natural form of pure carbon. It exists actually under certain thermodynamic conditions of temperature and pressure. What number of atoms of carbon are in a 1 carat diamond? 1 carat means actually 0.2 gram. So now you're given the mass in this case, and you can do this exercise at home. You just rearrange that equation and solve for the number of atoms based on the given mass, right? So you already see that this is quite useful, right? You can always, from the mass, you can always estimate how many atoms you have in there, right? Assuming that it's pure and ideal, and you can always estimate how many atoms you have. Okay, another join in. Which of the following is the most accurate description of a mole? A, the mass of carbon in the measured sample of carbon. B, the number of atoms in any given mass of an element. C, the number of sodium atoms in 58.44 grams of sodium chloride. And these two are accurate descriptions. Okay, so who thinks it's A, B, C, D? Maybe think for a moment more. Okay, who thinks it's A? So A is saying mass of carbon, right? But mass has nothing to do with mole. Mole has something to do with the number of particles. Yeah? Right? And n is the mole number. N is proportional to the number of particles. Right? So, of course, they are also proportional with the mass. Right? That's also true. More particles, the higher the mass. But in this case, we were out to search for a definition of a mole, which is not directly related to which is not the mass itself. It's related, but it's not the mass. How about B, the number of atoms in any given mass of an element? And that cannot be true because one mole is a very distinct number of atoms, right? How about C, the number of sodium ions in 58.44 gram of sodium chloride? Well, for that you need to calculate the molar mass of sodium chloride, which apparently is 58.44 gram per mole. So you just add the mass of sodium and chloride together, and you will see that this exactly equals 58.44. Okay, so the molar mass of sodium chloride is 58.44 gram per mole. This means if you have 58.44 gram, this is exactly equal to 1 mole. Okay, this is the right answer. Okay, one more. Which of the following is closest to the average mass of one atom of copper? Okay, so look in the periodic table. What is the mass? Of course, I will ask you to memorize all the masses. All of them, not. You get a periodic table in the exam. Okay, so based on what you see there, what do you think is the right answer? Is it A, B, C, D, E? What is that? I cannot actually see it. 63.546. 63.546. So this is the average mass of one atom of copper, right? One atom, not one mole, right? So it's a bit mean question. So it's actually one atom. So for that you would need to. So how can you get this? Well, you know the mass of one mole, right? The mass of one mole is, what is it? 63.546 gram. Right? So one mole has this mass in gram. But now you want to know the mass of one atom, so you need to divide by the Avogadro number, right? And then you get this number. Yeah. So by dividing by the Avogadro number, you convert to the mass per atom. Right? Which of the following 100 gram samples contains the greatest number of atoms? Magnesium, zinc, silver, calcium, or all the same. To look into the periodic table again, check out some of the molar masses. Okay, who thinks it's A, magnesium, B, zinc, C, silver, D, cadmium? All the same, maybe? No. You just get the molar mass, right? Okay, so just use this equation, right? You have a fixed mass, M is fixed here, right? Then how do you get N, the number of moles? Number of moles is mass over the molar mass, right? This one is the same always, so this is only changing, right? So the largest mass you get if the molar mass is very small, right? And the smallest molar mass is magnesium. Yeah? Magnesium is the lightest. So you have the most atoms per mass. So magnesium is the right answer. So this is the molar mass of a substance, which is the mass in gram per 1 mole of compound. Okay, I think we finished for today. Everyone is exhausted, so see you guys next week. To remember. Great.